plane is inclined at an angle alpha to the horizontal. A particle is projected down the plane with initial speed of 10 meters per second at an angle of 45 degrees to the inclined plane. The plane of projection is vertical and contains the line of greatest slope. I'll just briefly mention what this last sentence means. The plane of projection is vertical. What is the plane of projection? That's the plane that contains the trajectory of the particle. So the dotted line is the trajectory. So you can imagine that embedded in a plane. A plane is a flat surface. This plane is vertical and it contains the line of greatest slope of the incline. So if you can imagine looking in this direction at the incline, what would you see? Well, you would see some flat surface, of course. It might be rectangular. This point here represents the point from which the projectile is launched. And Q must be directly below this launching point. So if we're looking at it, looking in this direction at the incline, the trajectory would appear to be a straight line. So that's what's meant by the line of greatest slope. The particle is launched in this direction, not in some other direction. If it was launched in some other direction, the slope would be less than the slope of this line here. This line has greatest slope. It's straight down the incline. Now, to analyze the motion of this particle down the incline, it's a good idea to take the positive x-axis pointing down the incline in the direction of motion of the particle. This angle here is alpha. So the positive x-axis is down the incline. The positive y-axis is perpendicular to the incline. Now we're interested in analyzing the motion of this particle. So we will be interested in the acceleration of the particle. So let's consider the particle at some position here. What's its acceleration? Well, we're assuming no air resistance. So the acceleration will be due to gravity. The magnitude of the acceleration is g, which is 9.81 meters per second squared. Now, we need the x and y components of this acceleration in order to analyze this motion. So again, like in previous videos, we will look at the motion of the particle as consisting of two linear motions. One linear motion in the x direction and one linear motion in the y direction. And the accelerations in both directions will be constant. So we can break our problem down into a problem of linear motion with constant acceleration. But two linear motions with constant acceleration. So we need the acceleration in the x direction and the acceleration in the y direction. Both of those accelerations are constant. So we need to get the x and y components of this vector here. So how do we get the y component? Well, we project the tip of this vector onto a line passing through this point that's parallel to the y-axis. So then we create two vectors that must sum to give g. So by the triangle law, the two vectors must look like this. So this component here is the y component of g. I will call it ay. So the acceleration is g. Well, the magnitude of the acceleration is g, which is 9.81. This here is the y component of g. You can see that it's parallel to the y-axis. This vector here is parallel to the x-axis, so it must be the x component of g. Now, we know the magnitude of g. We know it's 9.81. We have a right-angled triangle here. So to find ay and ax, we need an angle in this right-angled triangle. So the angle that we can get is this angle here. This angle here is actually the same as alpha. And I better explain why that's true. Well, alpha is an angle between two lines that happen to be perpendicular to this line and this line. the acceleration vector, the line passing through the acceleration vector, is a vertical line because the acceleration due to gravity is vertically down, so it must be perpendicular to this horizontal here. And a line passing through AY is parallel to the y-axis, and by definition that's perpendicular to the x-axis because we've set this up so that y is perpendicular to x. So the angle between a pair of lines that are perpendicular to another pair of lines is equal to the angle between that other pair of lines. So this angle equals this angle here. So that's worth remembering. Now, what is AX? Well, AX is the hypotenuse of this right angle triangle, which is G, which is 9.81, times the sine of alpha, because AX is opposite angle alpha. And AY is G times the cos of alpha, because AY is adjacent to angle alpha. We can get the x and y components of the initial velocity by multiplying 10 by the cos of 45 to get ux. So ux is in the positive x direction. Cos of 45 is 1 over root 2. So we get 10 times 1 over root 2, or 10 over root 2. That's this vector here. This is ux. And uy is the vertical component of the initial velocity. It's 10 times the sine of 45, or 10 over root 2. Now in this question we will be interested in the final velocity of the particle. That is the velocity of the particle just before it strikes the incline, because we're given some information about the angle that the final velocity vector makes with the incline. We're given information about this angle theta. We're given that tan of theta equals 1/4. So what we do is we use a formula for linear motion with constant acceleration. This formula gives us the final velocity in terms of the initial velocity. So we can apply this in the x and y directions. So let's apply it in the x direction. So the final velocity of the particle in the x direction is the initial velocity in the x direction, which is 10 over root 2, plus the acceleration of the particle in the x direction, which is g sine alpha, times the time. So for any time we want, we can get the velocity at the x component of the velocity of the particle at that time. So we just plug in for t, provided of course we know what alpha is. We actually don't know what alpha is, but here is Vx as a function of t. Alpha is some fixed value. Alpha is something we have to find actually, but t is the variable. T is the independent variable. Now we can do something similar for Vy. That's the y component of the final velocity. Now I need to make a correction up here. You might have noticed that Ay is in the y direction, but the positive y direction is this way, away from the incline. So since Ay is pointing in a direction that's opposite to the positive y-axis, Ay is a negative vector. So that's important. Ax is positive, it's pointing in the positive x direction, but Ay is actually pointing in the negative y direction, opposite this direction. So Vy equals Uy, which is 10 over root 2, plus Ay, which is minus g cos alpha, times t. Now here is the final velocity vector v. The velocity vector is always tangential to the trajectory. So if the particle is here, the velocity vector would look like this. It would be tangential to just touch this trajectory at one point. So wherever the particle is, if say we put it here, then this would be the velocity vector. It's on a line that's tangent to the trajectory, just touching the trajectory at one point. So here we have the velocity vector. It's tangential to the trajectory. This is the velocity at the instant before the particle strikes the plane. Obviously when the particle strikes the plane, the velocity changes. It could become embedded in the plane, so its velocity could go to 0, or it could bounce As a matter of fact, it does bounce in this case. So always keep in mind this is the velocity of the particle just before it strikes the plane. And we have written down the x and y components of that velocity. Let's show those components. Well, the x component, or sorry, the y component would look like this. We just project the tip of the vector onto a line that is parallel to the y-axis. And to get the x component, we just complete this triangle. These two vectors have to add to give this vector. So the directions here make sense because these two green vectors add by the triangle law to get vector v. So we have a right-angled triangle formed here. This angle in here is theta. You see it's an angle between this part of the trajectory and the incline. But the incline is parallel to this line here. This is the x component of vector v. So this angle equals this angle. They're called corresponding angles usually, because this line is parallel to this line. Another way I could have shown the components of vector v would be to draw the x component here and the y component here. Then it's even clearer that this angle in here is theta. It's vertically opposite this angle. And these two angles are z angles, z or alternate angles, because we have a z formed. Anyway, I'll go back to the original way I displayed it. Another consideration we need is the time of flight. To get the time of flight, as you've seen in earlier videos, we put y equal to 0. So at the instant the particle strikes the plane, or the instant just before it strikes it actually, Sy equals 0. But what is Sy? Well, we know that for linear motion with constant acceleration, Sy is equal to uyt plus a half ay t squared. So we need the y component of the initial velocity and the y component of the acceleration. And we put Sy equal to 0, and then we can solve for t. So the y component of the initial velocity is 10 sine 45, which is 10 over root 2. The y component of the acceleration is minus g cos alpha. So we have minus a half g cos alpha times t squared. So we can solve this equation to find the time of flight. We can factorize t out of this equation here. So if we do that, we will have this here. So the two factors multiply to give 0. So like you've seen before, we put each factor in turn equal to 0. If we put this equal to 0, we get t equals 0. That's just a trivial solution. The time when the particle is launched. So we put the other factor equal to 0. And what do we get? So this is what we get when we put this factor here equal to 0. We just rearrange then to get t. We bring the 10 over root 2 over to the other side, and we divide by the coefficient of t, which is a half g cos alpha. Of course we have minus signs there, but they both change. They both cancel to give plus. So this is the time of flight. And what we can do then is plug this time of flight in for t in both Vx and Vy. So we can get Vx and Vy in terms of alpha. So here is Vx. It's 10 over root 2 plus g sine alpha times t. So here is t plugged in here. The g's cancel. Sine alpha over cos alpha is tan alpha. And multiply above and below by 2 to get 20 over root 2 tan alpha. So that's Vx. Here is Vy with t plugged in. Luckily here the cos alphas cancel out, the g's cancel out as well. So I'll just write Vy over here. We get 10 over root 2 minus 2 times 10 over root 2. I've just multiplied above and below by 2. Multiply underneath by 2 to get 1, and multiply on top by 2 to get 2 times 10 over root 2. G and the cos alphas are gone. So we have 1 times 10 over root 2 minus 2 times 10 over root 2. Well, that's like 1x minus 2x. That's minus 1 times 10 over root 2. So Vy has come out to be negative, as expected, because it's a vector pointing in the negative y direction. So Vy comes out to be minus 10 over root 2. And Vx is 10 over root 2 multiplied by 1 plus 2 tan alpha. I just factorized 10 over root 2 out of Vx. Now we are given some information about the tan of theta. We're given that the tan of theta is 1/4. But we can see the tan of theta from this right angle triangle here. The tan of theta is the side opposite theta, which has a length of 10 over root 2. So we just drop the minus sign. We're just taking the length of this line here. And we need to divide that by the side adjacent to theta. Tan of theta is opposite over adjacent. So we get 10 over root 2 divided by this here. Tan theta is 1/4. That's what we're given. So now we can solve this equation to find tan alpha and hence get alpha. Alpha is the only unknown in this equation. To solve this equation, we can divide above and below by 10 over root 2. Then we can cross multiply, so 4 times 1 equals 1 times 1 plus 2 tan alpha. So 2 tan alpha equals 3. Tan alpha equals 3 divided by 2. Inverse tan of 3 over 2 is 56.31 degrees. If the magnitude of the rebound velocity at point Q is 5 root 33, find the value of E, the coefficient of restitution. So this is the point Q where the particle rebounds and it will follow some new trajectory. So we want the velocity vector immediately after the particle rebounds. So that velocity vector is perpendicular to the trajectory at this point. Its magnitude or length is 5 root 33. We don't know at what angle the particle rebounds at. Now let's look at the x component of the velocity of the particle before it rebounds. Well, we know it's equal to this here. We saw that earlier. But now that we know alpha, we can plug 56.31 in for alpha and break this down. The tan of alpha was 3 over 2 as you saw earlier. 3 over 2 times 2 is 3. 3 plus 1 is 4. 4 times 10 is 40. So we get 40 over root 2 for the x component of the velocity of the particle just before it strikes the surface. Now I'm going to change notation here. V now becomes u. V becomes the initial velocity. That's the velocity of the particle before it rebounds, and v, the velocity of the particle, is the velocity of the particle just after it rebounds. Letter u is normally used for initial velocity and v for final. So I will have to call this vector u now, so don't confuse the two. This new vector becomes v. We know its magnitude is 5 root 33. We don't know at what angle it bounces off the incline at. Now if you haven't done collisions before, I'll just give a brief rundown of the logic behind this. When the ball strikes the surface, there is no force in the x direction. The force on the ball or particle, whatever it is entirely in the y direction. That's an important fact. So that tells us that the x components of the velocities, these two velocity vectors, are the same. If there's no force in the x direction, then at the instant before the particle strikes the plane, the x component is this here, which we know is 40 over root 2. It will equal the x component of the velocity of the particle immediately after the particle strikes the plane. So here is the x component of vector v. So both of these are the same. They're both 40 over root 2. Remember, this happens over a very brief instant of time. Over the next few instants, the x component of v will change. But we're talking about the instant immediately before and immediately after the particle rebounds. immediately before and immediately after rebounding, the x components of these are the same because there's no force in the x direction. The force on the particle is entirely in the y direction. So it's the y component that changes. Here is a more accurate picture of the situation. As a matter of fact, Vy is less than Uy, because after the ball bounces, you can imagine some of its energy is lost in the bounce. The force is entirely in the y direction. So you would expect that the y component of the velocity of the ball or particle immediately after rebounding should be less than the y component of it immediately before rebounding. So you would expect that Vy would be less than Uy, and that is indeed the case. More accurately, I should say the magnitude of Vy will be less than the magnitude of Uy, because vector Uy is actually a negative vector. It's pointing in the negative y direction, whereas Vy is a positive vector. But if we just talk about magnitudes, we will have this relation, which makes intuitive sense if you imagine something bouncing. What I just said is reflected in this very famous result, experimentally shown to be true. It's called Newton's law of restitution. And it says that the magnitude of Vy equals some constant E times the magnitude of Uy. E is a number between 0 and 1, as you would expect. If we want the magnitude of Vy to be less than the magnitude of Uy, then we have to multiply Uy by some number between 0 and 1. This number E is called a coefficient of restitution. So, how do we find E? Well, to find E, we need to find the magnitude of Vy, the magnitude of this vector here. Well, we have a right angle triangle here, and we can use Pythagoras' theorem to find the magnitude of Vy. We can see that the magnitude of Vy squared plus the magnitude of this vector squared, which is 40 over root 2 squared, must equal the magnitude of vector V squared. Remember, this is vector V, and its magnitude is 5 root 33. That's what we were given. So this is just Pythagoras' theorem applied to this right angle triangle here. The missing side is the magnitude of Vy. Conveniently, the magnitude of Vy is 5. So 5 equals E times the magnitude of Uy. The magnitude of Uy is 10 over root 2. So E is 5 root 2 over 10, which is root 2 divided by 2. This 2 in the denominator can be written as root 2 times root 2. So we can write this number as 1 over root 2. And you can see 1 over root 2 is indeed a number between 0 and 1 as expected.